Learning objective 6. What if we don't have a mathematical formula? We don't have a research department or consultants. Well, we can use regressions. So you guys have learned some data analysis tools, and we're trying now to dust those off and use them here to illustrate how we can use regression to help us in estimating the demand function. And where would we get this information? We would get this information from observations. There may be public available information, or we may have to do it the old-fashioned way and do our own measurements in order to obtain data points on which to base our regression formulas. The first approach, as you probably remember, is the simple one. It's a linear regression, where we simply have one independent variable, which is x, and one dependent variable, which is y. The form looks a lot like the equation for a line, y equals a plus bx plus e, where e is a random error term for the model. And the least squares regression line is we have the intercept plus the coefficient for the first variable, and that's how we will look at the Excel results when we run a regression. So when we look at the output, typical output from Excel, we see a bunch of things here. So I'm going to walk you through this. Again, this may be a review for many, if not most of you, but I'll just go through it and make sure we're on the same page. First is, what is the formula? If we ran this linear regression, the formula is the quantity equals the coefficient, which is the constant, and here it's plus the coefficient for the first variable, but it's a negative, right? So it's negative 2.6, and then price is the independent variable. So the formula is easy, and Excel does a good job making it easy to pluck off because it just has the term of what it is next to the coefficient. Next, we'll look at how good is the fit. And we'll look at two measures. The first is r squared, which is the coefficient of determination. So it says how much of the total variation is explained by this model. And this is ranges between 0 and 1, with 1 being perfection, right? 100% match. Adjusted r squared reflects that sometimes we have issues with numbers of observations, or we clutter with lots of different coefficients. So here, an adjusted r squared looks at the data and evaluates it and adjusts it for the penalizing, if you will, for the lack of information or degrees of freedom. So let's look at those on the typical output from Excel. R squared of 0.75. That's not bad. It explains 75% of the variation. Adjust r squared is lower, 72, which is slightly lower. We could see in certain more extreme circumstances a big difference between r squared and adjusted r squared. In this case, we have sufficient number of data points such that it is just 0.72. Okay, so not bad. Next is we're looking at significance, where we look at standard error and confidence intervals. Standard error is how much of the estimated amount would vary based on true demand model. And the 95% confidence is given what is our plus or minus 2 standard deviations of how sure we are about this result. And here we have the range for the coefficients of this amount here. The standard error is 112 for the overall model. And for the first item, the constant, the coefficient, it could be as low as 1068 or as high as 2194. Pretty wide swing, actually. And in the case of price, it's the factor we get from the regression is negative 2.6, and 95% confidence would be in the range of negative 1.3 to negative 3.82. Right? So there's a fair amount of variation there, honestly, when we look at these coefficients and the ranges. All right, Tstat. So the rule of thumb is if the absolute value of t is greater than 2, then we're 95% confident that the parameter of the regression is not 0. It may not be precisely the number we cite, but it's not 0. In other words, there is a significant relationship between that factor and the model. The f-stat and p-value are related, where the greater the f statistics, the better the overall fit, and the lower the p-value, then we have a better fit. So higher f's and lower p's. So let's look at what happened. The Tstat They're both over 2 from an absolute value, so that's good. The p-value are very low, so that is good because the lower the better. And the f-stat here is quite high at 23.94. So these statistics seem to lend credence to this model being usable. The other type of regression is a multiple regression or a nonlinear regression. So nonlinear, as we've seen before, often we use a natural log. So that could be the factor that we use. Here we have, again, just one variable of p and one dependent variable of q, and this is nonlinear, right? So that's one aspect. We can run that through regression by taking the natural logs of the data. Next, we could have multiple variables. In this case, we have quantity of x that has price of x. We have the income level and the price of h all being factors here. All right, so those are examples of what we do. Or we have the combination where it's both multiple and nonlinear, where we have natural logs and we have 3 variables, right? There's no limit, only your imagination. So here's an example of a regression output for a multiple regression. So we have the output table here where we have the intercept, price, advertising distance. These are the 3 independent variables. So quantity equals 135.15, the constant, minus 1.4 times price, plus 0.54 times advertising, minus 5.78 times distance. And this relationship had a pretty decent R squared of 0.78, of 0.79, not 100% of course, but that's a regression that is respectable. And this is something we would use. Now, if we were to do the combination of multiple and linear, it does not affect how we run and how we interpret the results of the regression. What it impacts is how we input the data into regression. So instead of putting in the number, the base 10 number, if you will, we put in the natural log of that number. So it just has one transformation. That's pretty easy. We have the data, and then we right next to it do the natural log of that data and run the regression against the natural log. So if we have x and natural log of x, if we did a linear regression without the use of natural log, we'll just run it on the x. If we run a regression on the natural log, then we just do it on the next column over, which is natural log of x. And the rest of the process is the same. Let Excel do the heavy lifting. So in practice, trial and error leads to success, or at least we hope so. And we might have a progression like the following. Let's start with the linear regression just to see how price and demand relate to each other. Then we might start looking at other variables and do a multiple regression. Then if we see some more dramatic relationships, we can try using natural log in order to see if there's exponential relationships at play or combinations of variables in the numbers themselves. Quantitative demand analysis had these learning objectives. We looked at elasticities from an own price, cross price, and income standpoints. Then we had some other elasticities. We looked at advertising, but it could be a number of other factors. Advertising was just an example. Then we also looked at the variation between linear and nonlinear forms for the formulas and how we could use those in order to estimate elasticities and predict changes in demand given changes in the underlying values. And finally, we looked at, in reality, if we don't have a formula, what do? We can use our tools from regression to give us an estimate of what that demand function might look like. All right, so that's chapter 3, and I'll see you for chapter 4.